Hello. Quite a lengthy video on finding roots of complex numbers and finding complex roots. And because of that, I'm going to go through several examples. You might want to skip forward and see which parts help you. And what we're really talking about is trying to find the complex solutions to the equation z to the power n equals 1, or these are called the roots of unity, 1 being unity. And after that, we're going to go and extend it to z to the n power n equals z0, where z0 is some generalized complex number. In order to do this, we're going to use the polar form of complex numbers. I'm assuming you know that z equals r to cos theta I sine theta. We're going to also use de Moivre here, that cos the n theta plus I sine the n theta is cos of theta plus I sine theta to the power n. We're also going to help us derive a different way of describing complex numbers in polars. Here we've got r cos theta plus I sine theta, and we're actually going to see that we can rewrite that as r to the times e to the power I theta. That should be an I. Apologies, my engineering coming out there again. Okay, let's start by looking at this different format, this e to the power format. So if we start with z equals cos theta plus I sine theta, for simplicity I've made r equal 1 here, because I'm only really interested in what happens with theta. Because when I differentiate it by theta, I dz by d theta, my cos theta here becomes minus sine theta, and my sine theta here becomes cos theta. Now it's not immediately obvious, but actually that is a fact, has a factor cos theta plus I sine theta, and the multiple out the front of that is I. So if we have a look at that, our I cos theta here equates to our I cos theta there, and our I times multiplied by I sine theta gives us our minus sine theta there in the real. So if we rewrite that, dz by d theta equals I times z. Now we've seen a function that works like that before, haven't we? And that's e to the x. And if we took the function e to the kx and we differentiate it and find the derivative, we get k times e to the kx, that's k times f of x. So here, and we see that we've got an I out the front, and here we've got a k in the general circumstance. So here, what we've actually just said is that our k in our case must be I. So if dz by d theta equals I times z, then z must equal e to the I theta. Yeah. And if I extend that now by bringing our r back to generalize it, then r cos theta plus I sine theta must equal r to the e to the I theta. And we may find that this form of the writing a complex number in polars is actually simpler to use, and we'll have a look as we go through. Okay, well, I started by saying that we're going to look first at the roots of unity. Let's find the complex roots where z to the n equals 1. Now, if we're working in real numbers, then in this case we might know that z would equal 1. But actually there's other solutions to this, and we're going to use de Moivre to find those. So let's start by doing z squared equals 1. Well, we know what the answers to that are. There's z equals plus 1 and minus 1. Those are our two solutions, aren't they, if we did it just in real numbers? And well, let's have a look at that and write this in polar coordinates. We want to equate that. This function is z squared as a complex number. Well, that's a complex number in polars with r equals 1 and theta equals 0, isn't it? Because that gives us 1 times cos of 0, plus I times the sine of 0, which equals 1, doesn't it? Yeah. Okay, so if we equate those two here and we use our de Moivre, z we're looking at z squared, so we've got 2 theta here in the bracket, yeah? Cos 2 theta plus I sine 2 theta must equal cos 0 plus I sine 0. And therefore, if we equate those, we know r equals 1, but we also now know that 2 theta equals 0, and therefore theta equals 0. And if we put those two values in, we can see that that gives us our solution z equals plus 1, doesn't it? Because that's 1 times cos of 0 plus I sine of 0, and cos of 0 is 1, and sine of 0 is 0, therefore z equals 1. But we know there's a second solution. So how are we going to get that second solution? Well, we assumed up there that theta equaled 0, didn't we? But there is potentially another solution here. And that solution is, if we started from our number here, there's our z equals 1, yeah, we could actually go round and add 2 pi to it and come back to the same place, couldn't we? An argument of 2 pi. And then we could go round again and go to 4 pi and we come back, and 6 pi, etc. So actually we've got a large number of solutions here, because not only could our angle theta be 0, but it could also, our angle could be 2 pi, 4 pi, 6 pi, 8 pi, and 10 pi, yeah? Now if we take the 2 pi solution, then we know that's from our demoivre that our angle inside our cos is 2 theta, and if we equate that to cos of 2 theta, then we know that, sorry, 2 pi, we know 2 theta equals 2 pi, and therefore we know theta equals pi. And we could do the same thing if we chose the our argument to be 4 pi, then 2 theta would be equal to 4 pi, and therefore theta would equal 2 pi, yeah? And we can carry on doing this, couldn't we? And if we do that forever, we get all these angles. Theta could either be 0, pi, 2 pi, 3 pi, yeah? Or we could get the negative ones. We get minus pi, minus 2 pi, and minus 3 pi, and going on forever. But these are all duplicates. There's lots of duplicates. We've only got 2 distinct principal solutions, and that is the angle is either 0 or the angle theta is pi. And if you think about it, this one here, z equals 1 is where theta equals 0, and z equals minus 1 is where theta equals pi. Yeah, and therefore I've just written them in the e to the I format there so we can all see them. And as we can see, effectively they're both on our unit circle. They're the two ends of our unit circle, aren't they? One solution's here and the other solution's there. Those are our 2 solutions. Okay, so let's extend this and look at some complex solutions. Let's have a look at z to the 5 equals 1. And looking at what we looked at before, we're going to use this idea that our angle, therefore, for this equation here, if we looked at our cos in here, inside here, what's our angle there, plus our I sine our angle here? Well, we could have either, this angle here could be either 0 or 2 pi or 4 pi or any multiple of 2 pi. And if we compare that now to our demoivre, we know, because we're doing z to the 5, that we could rewrite our power as cos to the 5 theta plus I sine to the 5 theta. And that's got to equate to an angle from our list above, any multiple, any integer multiple of a 2 pi rather. We write that as 2 pi k, where k is the number of lots of 2 pi. Yeah. So if we make this equivalence, we know that 5 theta, so we should just quickly say r is 1 again, but 5 theta will equal to 2 pi k, therefore theta will equal 2 pi k over 5, yeah? So here we have again multiple solutions. Theta is either 0, 2 pi over 5, 4 pi over 5, 6 pi over 5, 8 pi over 5, and then we get to 10 pi over 5, which of course is 2 pi, brings us back to 0, or we could do it all with the negatives. Now, if we look at this, we've actually got 5 distinct principal solutions here for angles. We've either got 0, 2 pi over 5, 4 pi over 5, 6 pi over 5, or 8 pi over 5. And we can draw those onto our Argand diagram here, and therefore we have our 0 point. That would be like our base point, wouldn't it? And then we could go round, and in each one of these we're basically adding 2 pi over k, and so we're going round, aren't we? 2 pi over 5 rather, 360 over 5, what's that at? 72 or whatever degrees, isn't it? So we're going round 2 pi over 5 each time to get our other solutions. So actually we've got 5 solutions here, which is what we'd be looking for, isn't it? As we've got z to the 5, and they basically form a regular pentagon going around our unit circle. Yeah, so they've all got a modulus of 1, and they're all going round by 2 pi over 5 as we work our way round. So that gives us a nice, beautiful, symmetric way of finding our solutions. And if we wrote that mathematically, algebraically, we can either do it in the full cosine format, where here we've got 2 pi k over 5 as being our angle, or we could write it in the e to the I format, in which case z equals e to the I 2 pi k over 5. Yeah, and there's our 5 solutions. Okay, bit lengthy but worthwhile doing. And here you can think that any k we put into, any n rather we put into here, so here we had n was 5, so we've got a regular pentagon, but if n was 6 we'd be going up one, wouldn't we, to hexagon, and each time we get a nice symmetric regular polygon. Okay, let's extend this now and complicate matters a bit further by saying, rather than we're finding that z to the n equals 1, we're now going to do it for a generalized point complex number e to the I theta. I'm going to use that format because it'll be more practical. And let's use an example to start off with. So let's take our complex number that we're trying to equate it to, z to the 4 equals 16 e to the I theta. So if I drew a very quickly on a diagram, Argand diagram, I would have this point here. It's got magnitude 16 and it's got angle pi over 3, 60 degrees. Yeah, and we can think of it in the way we did earlier about finding our simple basic point, our first root, and then looking at this angle multiples problem. So let's do the basic point first. So z to the 4 will equal r to the power 4 e to the 4 theta, if we started off with a solution, and in this case we're going to have that as being 16 e to the pi over 3, and using our demoivre, we know that's going to be r to the 4 cos to the 4 theta, and that's got to equal 16 times this complex number, unit complex number, which has got an angle pi over 3. So if we equate our parameters here, then r to the 4 has got to be 16, so r's 2, and 4 theta has got to equal pi over 3, so theta is pi over 12. So if we look at that, we now know we've got a basic solution, that therefore z will equal 2 cos pi over 12, I sin pi over 12, which we could write as 2 e to the I pi over 12. And if I drew that back onto my little makeshift Argand diagram, I'd be looking at something, it'd be a point there, wouldn't it? So it's got modulus 2, and the angle is pi over 12, yeah? It's a quarter of the angle. So our modulus has become the fourth root, and the angle's been quartered, yeah? Because we're using n is 4. Okay. But as in the previous occasion, we could also start with our point, and we could go round an additional 2 pi. So all the time we could add our 2 pi's on, yeah. So we could either have pi over 3, or we can have pi over 3 plus 2 pi, couldn't we? And then plus 4 pi, etc. So if we do that, we know that our solutions are 2 pi 4 0, 2 pi 4 pi 6 pi, etc. And if we divide those through by we know that's going to be 4 theta using our complex numbers. And as we did before, we'd effectively, that would be 4 theta, wouldn't it? It would be 2, 4, 6, etc. So therefore theta equals, we're dividing by n, we're dividing by 4. So we got 0, 2 pi over 4, 4 pi over 4, and 6 pi over 4, which if we simplified, when we get pi over 2, pi and 3 pi over 2. So effectively we're turning around in 90 degrees here, aren't we? And we've got to add that part onto our base solution. So our new combined solution is our base solution, which is the 2 and the pi over 12 as being the angle, but we're also adding 2 pi k over 4, 2 pi k over n, yeah? Same the cos and the sine. So if we wrote that in the e format, we get 2 times e to the power I pi over 12 plus 2 pi k and 4, and in this case we'd be looking at using k equals 0, 1, 2 and 3 for our principal values. If we drew that on our diagram, our argand diagram here, we find we've got our base point, which we worked out. There's our 2e to the pi over I pi over 12, and then we've got 3 other points here, 1, 2, 3, each of which is a rotation of 90 degrees or pi over 2. So therefore we've got a regular square, a regular rectangle is a square. So those are, we've got 4 solutions. Effectively we've got our square and it's been rotated around, and it's been rotated around by angle pi over 12, hasn't it? And now we can extend and generalize that quickly, that if we took a generalized position that z to the n equals r e to the j theta, then using what we did above, we would see that our base point is going to be z, well, the magnitude or modulus is going to be the nth root, so that's going to be r to the 1 over n. And then our angle, well, if we're going to the nth root, then we're going to divide our angle theta into n parts, so we get theta over n. Or simpler to see here, that's r to the 1 over n plus e to the I theta over n. And then we've got to add on our incremental angles. So we're taking our 2 pi over k and we're dividing it into n parts, equal parts. Therefore our angle, our argument is theta to the n plus 2 pi k over n, cos, and then with sine. So the best way to look at it, a simpler way to look at it if you're comfortable, is in the e format. So we've got r to the 1 over n, e to the I theta to n, and then it's theta n, our specific solution, and then 2 pi k over n for our general solution, where k equals 0 up to 1, 2, 3 up to n minus 1. Yeah, and of course that would create a regular n-sided polygon rotated by angle theta over n clockwise from our real axis. So here we are with my quick summary of the situation. We can either go looking for the roots of unity, i.e. z to the n equals 1, in which case we're going to get a solution, our basic solution here, we get a cos and a sine, and the argument is 2 pi k over n. And if we did that for the 5th roots as we did earlier of unity, we would get a regular pentagon as we've got here on the right hand side, with our base point, our starting point, being here at z equals 1. And if we generalize that further and we looked at any general point e to the j theta, we would start by finding what the base solution is, base root is, r to the 1 over n, e to the I theta over n. That will give us our first point, which will be here in this example, and then we would find our other roots from there by our rotation round by 2 pi k over n. Each one's a rotation of 2 pi over n. So as we saw earlier, if we were looking for the 4th roots of 16, this z here, 16 e to the I pi over 3, we would have our 4 solutions here in a regular a regular rectangle or a square, and we would get that in all solutions. So it's quite a lengthy video, but hopefully that's of use and it covers an awful lot of ground.